On each slide, there's a question about a nuclear symbol. There's scratch paper up here if you want to write your answer down, ladies and gentlemen. But answer those questions, and then we will talk about them to make sure that we are getting what we need to. Okay? Questions, ladies and gentlemen? So that's where we're going to begin. That's our question of the day today, is to do slides 19 through 22, ladies and gentlemen. 19 through 22.
Are we finishing the video?
I got it queued up and ready to go, yes.
Like a mall. Yeah, like a cafeteria. Yes. Like the bottom parts are also. And then I don't know.
All right.
Right. Yeah. Like. I think it wasn't even like a minute. He like tried to. It was like I had it up with. Let's get now. The last time I was fucking yeah.
Somebody's dinging. All right, so a couple of things, ladies and gentlemen. Number one, tomorrow you will have a quiz. Your quiz will cover the following topics. It will cover electromagnetic radiation. It will cover waves, so you should know the parts of the wave. You should know what hertz is. You should know what amplitude is. You should know what unit frequency is in. You should know what a wavelength is. You should know the high point of a wave, the low point of a wave, the two different kinds of waves. It will be on nuclear symbols. And again, yesterday you did a nice job with that activity where you went back and you found the nuclear symbols, figured out how many protons, neutrons, and electrons were in. The one thing people still struggle with, ladies and gentlemen, the one thing they still struggle with is when you do the name in a nuclear symbol, you then include the mass number. Not the number of protons, not the number of neutrons, not the number of electrons. The name with the mass number after it, ladies and gentlemen. And the mass number is the one that is on the top of the symbol. Okay? So that is what we are at. Okay? I got the video that we will finish. And then I actually have an article that we will talk about where we're at, because that video was about 10 years old and they were still working on finishing that giant structure to cover up the nuclear reactors, and we will talk about that. Okay? And then today we're going to talk about the 3 different types of nuclear decays. We're actually going to get into talking about them. And then I have a little activity here that you're going to do where you're going to find one example of alpha decay, beta decay, and then an example of a stable isotope. So that's the plan for today. Questions? All right, so let's take a look at slides 19 through 22. After that, ladies and gentlemen, then we will get into the video from yesterday, the finishing of it. Okay? All right. Here's what I will tell you, ladies and gentlemen. One of the things that I am going to do is I'm going to take out a lot of the problems that have charges on them. We shouldn't have to worry about charge too much in this unit because we've already covered it in the unit where we talked about materials and resources and what the difference between things are, and we talked about reactivity. Don't need to worry about that at all for this problem, though. How many protons are in the following element? How many, Victoria? 90. This number on the bottom down here, ladies and gentlemen, is the atomic number. That is the number of protons in this atom. Okay? Questions? All right. So let's take a look at the next one. How many neutrons are in the following atom? How many neutrons are in this following atom here, Christian? Nope. Nope. Come on. Yesterday we did these. You found the neutrons.
90.
Nope.
235.
Nope. Good. We've eliminated all of those choices. The neutrons are found, ladies and gentlemen, by taking the top number minus the bottom number. Okay? So this number up here is the mass number. It is the number of protons plus the number of neutrons. And we asked you to write this down on your periodic table yesterday. By the way, someone did write this down on their periodic table yesterday, but at the end of class, this was left at one of the stations on this side. So if you think this is yours, ladies and gentlemen, you want to come up and grab it so that you have it for the quiz, because it has some notes on there that you will need. This number that is on the bottom here, ladies and gentlemen, that is the atomic number. The atomic number is the number of protons. So if we take these and we subtract them, we are left with the number 145, and this is the number of neutrons. Okay? So that is the number of neutrons, ladies and gentlemen. Again, I told you this yesterday. I will tell you this again today, and I am stressing this to you. People will look at this and go, well, Mr. Brand, on the periodic table, thorium, shouldn't that be 232 for the mass number? No, it shouldn't. This is an individual isotope, one atom of thorium. Thorium has multiple different isotopes. There's thorium-232, thorium-235, thorium-236, thorium-233. I can give you any of those. But when I give you this information, ladies and gentlemen, the only thing you cannot find by this symbol is the name. You can find protons, You can find neutrons. You could even find electrons. And you can find the mass number. All just by looking at this symbol. So do not go to your periodic table and look up mass number. Okay? Questions? Now, some of you have pointed out to me, and I completely understand this, and I wish I had a better copy for you. It is sometimes hard to read the names on your periodic table. They get a little blurry, they get a little bit smeared. Do your best with spelling them out as best as you can. I'm not going to mark it wrong if you put an M instead of an N or an N instead of an M. You just have to get close, okay? And I will give you credit for it, okay? The other thing is, on a quiz, on a test, you can call me over and say, Mr. Bragg, how do you spell this element's name? And I will spell it for you, okay? You just have to tell me which one. Questions? Okay, good. By the way, the correct answer there was 145. The 235 minus the 90, did I say 245 just now or 145? Sorry, 145. 145 by subtracting these two numbers in front, that will give you the number of neutrons. Okay? Now, here's what I will tell you. I've taken out, oh, sorry. I went back one and I went back too far. Okay. I've taken out questions like this. I'm not going to ask you about the number of electrons. Okay? If I do, it will be a neutral atom. So let's imagine for a minute, ladies and gentlemen, that instead of this being a +2, this is a neutral atom. Okay, now, how many electrons does this neutral atom of thorium now have, Mariana? 90, the same as the number of protons. The same as the number of protons, okay? Can somebody tell me how many it would be if it was a +2 charge?
88.
Okay. If it was a +2 charge, there would be 88 electrons. Why? There have to be 2 less electrons than protons to give us a +2 charge. Okay? If it is a 0, they have to be the same, and that's why they would both be 90. Okay? Questions? All right. All right. I think I have one more. The number 235 in the symbol represents which one of the following, ladies and gentlemen? So the number down here, this 235, which of these 4 does it represent? B? No.
D.
It represents D, the mass number. It represents D, the mass number. Okay? So again, ladies and gentlemen, I would write this down because we seem to be getting this confused. This number up here is always the mass number. By definition, the mass number is the number of protons plus the number of neutrons. That's what mass number is. It's describing how many of those pieces are in the nucleus. Now, the reason that's important, again, is in a minute we're going to talk about the 3 types of nuclear decay. In the 3 types of nuclear decay, this mass number can and will change in at least one of the 3 types of nuclear decay, which means you are going to change around the number of protons and neutrons in an atom. Okay? The number down on the bottom, and again, I would put this on my periodic table so that I have it. This is the atomic number. That is the number of protons only. Okay? That is the number of protons only. So, when we take and we subtract these two, the number that we get here is the number of neutrons. That's what we get there, ladies and gentlemen. Okay? And then finally, ladies and gentlemen, to do the name is the element followed by the mass number. So, for example, this is thorium 235. Okay? So, again, the only thing I need my periodic table for is to figure out that TH is thorium. That's it. Otherwise, everything else, protons, neutrons, electrons, mass number, all given there for you, ladies and gentlemen. You do not have to do anything with your periodic table. You can simply look at the symbol. Questions? Now, again, some of you, hopefully you now have this down. Hopefully you have this written on your periodic table so that tomorrow on your quiz, you can have that information handy. Questions? All right. All right, ladies and gentlemen. Then today we are going to take and we are going to do our end of our video that we were watching yesterday. All right. Anything about the video shocking, questions, things like that so far? Shocking questions? No, none, zero, zip, zilch. All right, we got about 5 minutes left of it, ladies and gentlemen. Please close your computers. Just shut the cover on them so that I know you're actually watching up here. Okay? All right, here we go, ladies and gentlemen. Here we go, here we go, here we go. Oh, this is about where we left off. There we go. Gosh, again. All right. So, questions, ladies and gentlemen. That that was shown in 2014, ladies and gentlemen. So that was about 10 years ago. Obviously, they were running. They had yet to complete that project. Okay. This now I need to find it. This is the latest update on it, and this was from 2019, September 20th, 2019, 5 years ago. They basically finished the structure. So this is what is now covering the entire nuclear plant. Okay. So the accident happened on April 26th, 1986. They built a very crude covering for it that they called the sarcophagus to stop the spread of contamination. Okay. That sarcophagus wasn't intended for long term. It was basically, let's cover this stuff up. Let's make sure it's not leaking radiation anymore. Let's make sure it's not hazardous. So then they started to dismantle it and take it down before it comes down after they put up this new building. Okay. So, again, they had a lot of problems with it and things like that. Where is it at? So, again, cleaning up things like that they were trying to do, couldn't get to some of it because it was highly radioactive. They put in 400,000 cubic meters of concrete. Okay. 400,000 cubic meters. Now look at the floor below you. And if you see an area 9 tiles, 3 tiles by 3 tiles, that's a yard. Now imagine going up those 3 tiles and making a cube that size. That's 1 cubic yard. A cubic meter is just a little bit bigger than that. They used 400,000 cubic meters of concrete to try to cover this. It took 7 months to get done just so that they could stop it. Again, the workers there had to work in shifts where they would work for a while and rest for a while, work for a while and rest for a while because they couldn't be exposed to too much radiation. 31 people died from acute radiation sickness, and that was the people who had been working on sealing it up. So in 1998, they decided that they needed a better structure, and that is when they started building the giant sarcophagus that you saw the other day. So here it is. They're constructing it. I mean, you think about it, ladies and gentlemen, nowadays we have stadiums that have retractable roofs and things like this. This would be like moving the entire stadium, though, if not more. Okay? So engineering has come a long way, ladies and gentlemen. Okay? So they built a 320-ton outer shell. It was about 1,000 feet away. Yesterday, he said it would move about 30 meters an hour. Or I'm sorry, 10 meters an hour. That's about 30 feet. So every 2 minutes, you are moving basically a foot to put that into place. Okay. They finally did finish it, ladies and gentlemen. The new structure is designed to last about 100 years. So I guess you won't have to worry about it. I won't have to worry about it, but somewhere down the line, someone's going to have to worry about it again. Okay. And the framework was put in place in 2019. It was completed and rolled into its final location in November of 2016. So for the last 8 years, it has been in place, making sure that it would basically keep us safe. So that's where we're at with it, ladies and gentlemen. It is done. It is complete. It is in place. Okay. One of the things about this was this happened because of an accident at the plant where they were running a test. The nuclear plants in Russia were designed very differently from nuclear plants in the United States. And that is why, while people were worried, people in the United States were not. There wasn't the same design that it was there. However, in the video we showed you about 3 Mile Island, the nuclear guy, the regulator, said that the power plant in Japan was American design, and yet they still had an accident there because of the tsunami that destroyed it. One of the things is you've got to build these things near water because you need water for them. The problem is building them on an ocean where a tsunami can occur, probably not the greatest move. So anyway, ladies and gentlemen, that's our part on the Chernobyl. I do have one other part that we'll show you a little bit tomorrow on it. One more follow-up on it, so just so that you know. Questions? All right, if you would, ladies and gentlemen, open up your computers and get to EISN slide number 23. And that is this. Okay? So we're going to start by talking about alpha decay. Okay? We're going to start talking about alpha decay. There are 3 types of nuclear decay, and they are all very different from each other. During nuclear decay, you're literally changing the nucleus of the atom, ladies and gentlemen. You are changing the nucleus of the atom. Okay? And the first type of decay is called alpha decay. Now, in alpha decay, what happens is there is a nuclear decay. That is a spontaneous breakdown of the atom's nucleus into new atoms releasing energy. And it is the energy part that is dangerous or useful to us. If you are talking about a nuclear reactor that will make power for a submarine, if you are talking about a nuclear reactor that will make power for a battleship floating in the ocean, we're using that for good. If you're talking about a nuclear reaction that releases energy in the form of a nuclear bomb, you are talking about using it for bad, okay? Or good, depending, I guess, which side of the aisle you're on, okay? But the releasing of energy is one of the things that happens during nuclear decay. Now, an alpha decay goes by the Greek symbol alpha, which looks, to me, it looks like a fish. Okay, kind of like you would draw a fish when you were a kid. There's its face, there's the tail end, but that is the Greek symbol alpha. Okay, and during alpha decay, what happens is the nucleus breaks apart and it releases 2 protons and 2 neutrons from the nucleus. That is what goes flying out of the nucleus, these 2 protons and these 2 neutrons. Now, that is what we call an alpha particle. That is the piece that literally leaves the atom. Okay? Now, if you think about it, this new piece of matter has 2 protons in it and 2 neutrons. We're not worried at all about electrons. Don't worry about that. Okay? But if some piece of matter has 2 protons in it, what is that matter called? What do we call any piece of matter that has 2 protons?
Electron? Oh, no. Ion, cation?
It would be an ion and it would be a cation, you're correct. But a piece of matter that has 2 protons in its nucleus?
Hydrogen.
Nope, close. That's a helium atom, ladies and gentlemen. Helium has 2 protons in its nucleus. So what happens is, literally an atom loses 2 protons from its nucleus. That means the number of protons go down. Okay? That means the number of protons go down. This alpha particle, though, is positively charged. Why? Because it's only got 2 protons and 2 neutrons. It doesn't have electrons that go with it right away. So you've got 2 protons, 2 neutrons. You've got a positively charged particle. The atomic number of the original atom decreases by 2. It goes down by 2. In other words, when we balance a chemical reaction, we say you have to have the same number of each kind of atom on both sides of the reaction. We don't do that here, but we do need to account for all of the atomic number and all of the atomic mass. So if this new helium atom takes with it 2 protons, the original atom then goes down by 2 protons. What that means, ladies and gentlemen, is if there is an isotope of uranium, it happens. An isotope of uranium and it loses 2 protons, what does it become? So a uranium atom splits apart. 2 protons go flying off as a helium ion. What's left?
The T8, maybe the element T8.
You got it. The element thorium. Why? Well, there were 92 protons, 2 of them left. Now you've got an atom with 90 protons. That is thorium. So literally on the periodic table, an element will back up 2 spots if it undergoes alpha decay. Lead would become mercury. Seborgium would become Rutherfordium. You back up 2 spots because of the alpha decay. Okay? So your atomic number decreases by 2. Now, what else changes though? The mass number. By how much?
4.
By 4, and it goes down by 4. Why 4?
What if we can't do it to hydrogen because we can't back up 2 hydrogen?
Correct. Hydrogen cannot undergo alpha decay. You are absolutely correct. Why?
Because it's the first element on the periodic table.
Yeah, it can't lose 2 protons because it doesn't have them. Hydrogen cannot undergo alpha decay. Actually, neither could helium. Why?
Because in the first valence electron cell.
It doesn't have 2 protons to lose. So again, normally radioactivity occurs with larger atoms. Okay? Bigger atoms. Things that are further around on the periodic table. The first few elements, some of them are radioactive. They have radioactive isotopes. But again, they can't undergo alpha decay because hydrogen cannot lose 2 protons. It doesn't have them. Helium cannot use 2 protons because if it does, there's nothing left. Even lithium. I guess lithium could undergo alpha decay, but what would it become?
Hydrogen.
So lithium is the smallest atom that can undergo alpha decay because it is the smallest one that could lose 2. That doesn't mean it does. That only means that it could. Okay? Questions? So this is what a alpha decay would look like, ladies and gentlemen. So you start out with an atom. This is radon-222. It undergoes alpha decay. It gives off an alpha particle. So this 86 then becomes what? If you lose 2 of these, becomes 84. So if you look, this number over here still has to be balanced off by these 2 numbers down here. 2 and 84, 86. We're still accounting for every proton that was there originally. They're just in different spots now. This 222, this mass, has to be accounted for as well. Well, 4 of it goes here. Why 4 again? Go ahead, Ethan.
Oh, God.
Anybody?
Because the mass is decreasing by 4.
I agree with you. Absolutely. Why is this got a mass of 4?
Because the atomic number is decreasing by 2.
I'm agreeing with you. Okay? But what about this particle? I understand the 2 protons have a mass of 2. Why does this have a mass of 4?
I think you take the top number minus it by 4.
Take the top number here,
Yeah, and minus 4.
and that gives you what?
218.
Good. Perfect. I understand that. But you still haven't told me why this is 4.
Because it's as it is.
Subtract the numbers in front, ladies and gentlemen. What do you get?
So if you do 218 minus 4, that's going to give you, or 222 minus 4 is going to give you 218.
Correct, and that's how we'll get that. We're going to show you that later. What is the top number in front of helium represent? That 4. What does it represent?
Mass number.
Which is what? So why is it 4? Because you not only lose 2 protons, but you lose what? Nope. 2 neutrons. Remember, the piece that breaks off, not only does it take 2 protons with it, it takes 2 neutrons with it as well. That's why you get a mass of 4 here. 2 protons and 2 neutrons are going. They're leaving the nucleus. That leaves the nucleus with fewer number of protons and a fewer number of neutrons in it. So you're right. You guys were all on this. This number plus this number has to equal that one. Yes, absolutely correct. This number plus this number has to equal this one. Yes, absolutely correct. Questions? Okay? All right. So this is what is called alpha decay. Here's another example. Osmium 186 undergoes alpha decay. Here's your alpha particle. You have 76 protons originally. 2 of them are here. That means 74 are here. What's W on the periodic table, ladies and gentlemen?
Tungsten.
Tungsten. 186 is the mass number here. 4 of it is here. That means there's 182 left over for here. By the way, each different isotope only undergoes a certain type of nuclear decay. So osmium 186 only undergoes alpha decay. It does not undergo beta decay. Only alpha decay. And when it does, we can tell what it creates. Okay? Now, if this that is created is radioactive, it may break down again. Might go through one of the 3 kinds. If not, this is a stable atom and nothing happens to it. Not every atom breaks down. All right. So the second type of decay, ladies and gentlemen, is what is known as beta decay. Okay? Beta decay. Now, the Greek symbol for beta is just a fancy B with a nice long tail on it. Okay? That is the symbol for beta. Again, the nucleus breaks down, ladies and gentlemen. But now, something different happens. Now you don't lose 2 protons and 2 neutrons. Now, ladies and gentlemen, a neutron in the nucleus becomes a proton and an electron. So literally, a neutron in the nucleus breaks apart. Okay, a couple things here. What's the charge of a neutron? What is it? Nope. The charge is neutral. It doesn't have one. So when it breaks apart into a proton, which has what kind of charge? Positive. And an electron, which has what kind of charge? Negative. This is what leads scientists to believe, ladies and gentlemen, that protons, neutrons, and electrons are not the smallest part of matter. Because if a neutron can break apart into a proton and an electron, that means that there might be other smaller pieces out there still. Okay? But think about it. Neutron, no charge. Proton, positive. Electron, negative. What do a positive and a negative charge do to each other?
Cancel out.
They cancel each other out. That's how they make a neutron. No charge. No charge. Okay? Now, a couple of things. Where are neutrons located?
The nucleus.
They're located in the nucleus. So now all of a sudden, out of the blue, this atom has a neutron break apart into a proton and an electron. Well, where are protons in the atom? Where do they belong?
The nucleus.
They belong in the nucleus. Boom, there's an extra proton. Cool, wonderful, awesome. But now in the nucleus there is also a what? Yeah, we don't care, we just said that. There's a proton there. Whoa, big deal, there were protons there before.
Electrons.
Now there's an electron in the nucleus. What's the problem with that?
There shouldn't be an electron and a neutron in there.
Well, neutrons are fine in there.
Well, electrons shouldn't be in
There shouldn't be an electron in there. So that electron gets shot out of the nucleus. You don't belong here. Get out. Get out. Go away. Okay? Now, when that happens, ladies and gentlemen, that electron is what we would call the beta particle. It's the part that goes off from the nucleus, and with it, it takes energy. Energy that can be harmful to you. Okay? So this beta particle goes shooting out of the nucleus, which is basically just an electron going off into space. Okay? Going off into space. Okay? So the particle has a negative charge. The last one had a positive charge. Why? Because it was 2 protons. This is the negative charge. Why? Because it's an electron. So what happens to the number of protons in the nucleus during this reaction?
It increases by 1.
It increases by 1. The atomic number actually goes up by 1 instead of down by 2. Okay? It goes up by 1 instead of down by 2. So if you have an element on the periodic table like francium, if it were to undergo beta decay, what would it become?
Radium.
It would become radium. During alpha decay, we move back 2 spots. During beta decay, we move forward 1. We move forward 1, ladies and gentlemen. Okay? What happens to the mass number here?
It does not change.
Why? Why does the mass number not change? You lost a neutron. What should the mass number do if you lose a neutron, Alex?
Go down.
Go down. How much? 1. You have 1 less neutron. It should go down by 1, correct?
there.
Well, what did you create? What happened to that neutron? What did it become?
Can be positive.
What?
I think it became a positive.
Which is called a what? What's a positive particle in the nucleus of an atom called? A proton. What's the mass of a proton?
1.
1 AMU. So we lose 1 AMU because the neutron is gone, right?
Right.
But a proton is created which has a mass of?
1.
So what happens there?
Nothing.
Nothing. It stays the same. It's equal. What's the mass of an electron? Basically none. None. So does it change the mass of the nucleus? No, it does not. The mass number does not change here. The mass number stays the same. You have lost a neutron, yes, but you have gained a proton. They have equal masses. That means no change. The electron goes flying out of the nucleus. It had no mass, so we don't care. We don't care. Now, when you look at this, this is kind of a weird thing here, ladies and gentlemen. What does the E mean?
Electron.
Electron, because that's what a beta particle is. So up on the top here, you have 207. What happens to the mass number during a beta decay?
Nothing.
So what do you end up with?
207.
Same number. How do you get a -1 here, though? Nope. That's a good guess.
Because of the negative.
That is a good guess, but it is not because of the negative charge.
That's what I was gonna think.
What number is that on the bottom? This is the mass number. Okay. Why is it a -1? How can you have a -1 proton?
Because probably the one that got kicked out.
Which one? What got kicked out?
The electron.
The electron did. What's left behind?
The
A
negative.
proton, which means you have one more, correct?
Yeah.
One more, right? Well, look at the number here compared to the number here.
Goes up.
It goes up by 1. The only way we can mathematically put a number here to make this go up by 1 is to put this as a -1. Because 84 plus a -1 equals 83. So this is a negative number, not because it is lost, but because that proton is left behind. There's one more there than there was. In the last one, this was a 2 here. Why? Because those 2 protons were gone. Here, this is staying behind, meaning this is going to be higher. So it's not like there is a -1 proton here, but there is one more left behind in the atom that wasn't there before. That's our way of accounting for it mathematically. Okay? So here you go. Here's carbon, ladies and gentlemen. Carbon 14. If it undergoes beta decay, you end up with nitrogen, 7 protons, same mass number though, 14 for the number. Now again, this is different than anything we've done before. In chemical reactions, you would never have one element become another. Only in nuclear reactions, ladies and gentlemen. Only in nuclear. Questions? All right. So one more type of decay, ladies and gentlemen. One more type of decay for us, and that is this. There's what is called gamma decay. Now, gamma looks like a real fancy Y. That is the Greek letter for gamma. Okay? Kind of a fancy Y. All right? Again, I'm not expecting you to write these. Hopefully you can recognize them, but I would put them down on your periodic table. During a gamma decay, the only thing that happens is the nucleus just gives off energy. Randomly gives off energy. There is no change in the atomic number. It doesn't become anything different. There is no change in the mass number. Everything stays exactly the same. Exactly. Okay? Nothing changes. So the changes have no effect on the nucleus. They stay the same. Here's how we would write it. Barium-137. If it undergoes gamma decay, guess what? Still barium-137. No change in the mass number, no change in the number of protons. Everything stays the same. All it did was give off energy. That is what gamma decay is, ladies and gentlemen. Just the giving off of energy. Questions? These are the easy ones. Why? What you start with is what you end with. Iodine-131 undergoes gamma decay. Guess what? Still iodine-131. Doesn't change. Doesn't become anything new. Now, questions? Sure. Dave?
So what does like that decay do then?
Just gives off energy. Just gives off energy. That's it. Doesn't become anything new. Just gives off energy. We don't know why. Just what it does. So these ones give off energy, but they don't change. So which of the three is the most dangerous? Why?
Well, because it does not change at all, but still, it could kill you.
Good catch, Kevin. The other ones, when they undergo decay, they become a new element. That new element may or may not be radioactive. If it's not, done. Can't give off any more energy. But gamma never changes. In other words, when it gives off energy, it can do it again later on, and again later on, and again later on, because it doesn't actually become anything different. So of the three, this is the one that is, in a way, the most dangerous because it doesn't become anything else. Okay? It doesn't become anything else. All right. So here's the summary, ladies and gentlemen. Now, again, I'm going to ask you questions, not on your quiz tomorrow, but on a test later on. So you want to make sure you've got this in your notes, ladies and gentlemen. These are two symbols that you can use for alpha decay. I think I have them in your notes for you, correct?
Yeah, the symbols.
Okay, good. Do I have the type of decay?
No.
Good, put it in. Alpha. The type of particle is alpha. The atomic number is -2, the mass number is -4, and the charge is positive. Copy that down. So again, this summary, ladies and gentlemen, not this quiz, but your next quiz, you will be asked about these. You'll be asked if this undergoes alpha decay, what is created? What is an alpha particle? What does it do to the atomic number? What does it do to the mass number? By the way, this is what it does to the original atom. The mass number goes down by 4. The original atom, the atomic number goes down by 2. Why? Because that was that helium particle that left. The second decay is beta. You will either have the symbol for beta or we will have electron with a 0 and a 1 and a -1 down below, ladies and gentlemen. Type of decay is beta. We call it a beta particle. The atomic number increases by 1. The mass number does not change and the charge would be negative, ladies and gentlemen. The charge of the particle would be negative. And finally, ladies and gentlemen, I'll let you copy that down before we just talk about or review it real quick with you.
It would be fun if we actually got to work with them, and like how we did in the back yesterday
What do you mean?
with like the cable.
Oh, so predicting the decays or whatever?
Yeah.
Well, maybe. Maybe. Again, just so you know, this is not on the quiz tomorrow. These alpha, beta, and gamma decays are not on the quiz tomorrow. Tomorrow. Tomorrow's the quiz.
Yeah, put them on the table.
Okay? Questions? So this basically covers all of this, what we just did on that last slide, ladies and gentlemen. Any questions? Okay. Please remember gamma, nothing happens. There's no change in atomic number, no change in the mass number. There's no charge to it because it's just energy. Okay. All right. So, ladies and gentlemen, these are some examples of different elements that undergo the different kinds of decay. So, alpha decay, radon 222, francium 221, osmium 186, bismuth 209. Beta decay is carbon 14, potassium 40, lead 210, and bismuth 210. Gamma rays would be barium 137, iodine 131, cesium 137, and cobalt 60. But there are a lot more, ladies and gentlemen, a lot more elements that undergo decay. So that is where you are going to come in right now. In Google Classroom, ladies and gentlemen, there is a sheet that says nuclear decay worksheet. Click on that. It's not actually a worksheet, ladies and gentlemen. What you are going to do is you are going to go to the resource ptable.com/isotopes. Now, this is a shared document. You all have access to it. You are going to write your name here, and then you are going to give me an example of an isotope that undergoes alpha decay. How do you find that? That is where this link to the P table comes in. So if you open up that link, ladies and gentlemen, it should take you to this, which is the isotope page. Make sure isotopes is highlighted at the top. Now, if you look in here, ladies and gentlemen, a yellow box around something means it undergoes alpha decay. A blue box around it means it undergoes beta decay. And a black box around it means that it is stable. You can pick whatever element that you want, any element you want. You click on the box, and you will get to see all of the different isotopes of it. So when you get to one where it is a black box around it, that means that it is stable and it will not change. Okay? So for example, calcium 42 is stable and does not change. Well, you're looking for ones that have a yellow box around them, a blue box around them, or a black box around them, because there are 3 pages to this assignment. On the first page, you're going to do alpha decay. On the second page, you are going to do a beta decay. And on the third page, you are going to do something that is stable. Now, you'll notice that when it's stable, there is nothing that it becomes, right? Because it doesn't change. Okay? It doesn't change. Okay? Now, you could find one element that has 3 isotopes that do each of these possibly. Or you can just click on them until you find one that has a yellow box around it or has a blue box around it that undergoes either beta decay or alpha decay, or a stable, and you can put it wherever you would like. So when you're doing this, ladies and gentlemen, I don't guarantee that you will always find every element that undergoes alpha decay. And by the way, don't use the examples I already gave. Okay? Don't use the examples I already gave. I will tell you this, the lighter the element, you may have a harder time finding nuclear decays with it. So for example, lithium, no decay, stable, stable, no decay, green, neutron emission, that's it. So lithium does not undergo alpha decay and it does not undergo beta decay. If you're struggling, go to the bigger elements, ladies and gentlemen. Now you will find some of those that undergo alpha decay and beta. Here's one that undergoes alpha decay, ladies and gentlemen. Why? Because when I'm on it, there's a yellow box around it. So all I'm asking you to do to finish up for today, ladies and gentlemen, is find one example of each, put it in the document, then you're done for the day, ladies and gentlemen. By the way, if you want it, there is a Quizlet online for the quiz tomorrow, ladies and gentlemen, that will help you review.